Hello everyone, welcome to this presentation. Before that, please introduce myself. My name is Debora Engelien Jaya with name 1212143, and I'm from Department of Chemical Engineering, Faculty of Industrial Technology, Universitas Nasional Yogyakarta in Indonesia. And this journal presentation was made with the aim of fulfilling the assignment of the processing technology for essential oils course, and our lecture is Dr. Heri Septya Kusuma, Sarjana Science, Magister Technique. On this occasion, it's my pleasure to share with you what I believe is an impactful study that I hope will influence your practice as it's influenced to mine. So, what do we talk about in today's discussion? First of all, I'd like to introduce the article, the authors, and the journal that the study was published, and I will discuss the outline of this journal, materials and methods, results and conclusion, and lastly, I'll share how I believe that the study has informed in my personal practice, but also potentially for the journal output. Onwards to this article, the title of this journal is Ultrasound-assisted extraction and properties of polysaccharide from Ginkgo biloba leaves. And this study, there are six authors, as we can see here in the screen, and they are Junchili Changsuan Chen, Hui Minse, Chiayu Kang Liang Wang from Key Laboratory of Carbohydrate Science and Engineering, Tianjin Key Laboratory of Inorganic Functional Materials, Tianjin Normal University, Tianjin 41331, China. And the last authors is Wang Huang from School of Chemistry and Environmental Engineering, Key Laboratory of Green Chemical Process of Education, Key Laboratory of Nuclear and Green Chemical Technology of Hubei Prince Wuhan Institute of Technology Wuhan 430074, China. This article was published in the Journal of Ultrasonic Sonochemistry, and also we can find out how to optimize the condition of ultrasound assist extraction of gingival polysaccharides using response surface methodology atau introduction. Recently, ultrasound assist extraction has been widely covered for its compliance with the concept of green chemistry and economic chemistry, and it has been greatly used for uh, we compare this method to the traditional extraction method. Ultrasound assist extraction have many benefits. Are take less time, requires lower temperatures, and has higher extraction efficiency. So, ultrasound assist extraction is suitable for the extraction of some temperature-sensitive products. Meanwhile, it is simpler and more economical than some emerging extraction methods such as microwave extraction, supercritical fluid extraction, enzyme extraction, and etc. Hmm, the principle of ultrasound assist extraction is based on the ability of ultrasound to produce cavitation, thermal, and mechanical effects, among which cavitation is considered to be the most important factor. So, when the ultrasonic wave acts on the extraction solvent, the liquid in the solvent will be torn into many small cavities in some areas of weak tension, and these small cavities will rapidly expand and close so that the violent impact between the liquid particles occurs. Mm, And of course, this impact uh, can easily break the plant cell walls, thus releasing intracellular substance into the extraction solvent, while thermal and mechanical effects also contribute to this process. So it has been well documented that ultrasound assist extraction not only increase the extraction rate, but also improves the activity of polysaccharides extracted by ultrasound. And in view of this, the algorithm was used to optimize the condition of ultrasound-assisted extraction of polysaccharides from ginkgo biloba leaves. And RSM is a statistical method to find the optimal process parameters and solve the multivariate problems through the analysis of regression equation, so which is commonly used in the design of natural product extraction experiments. These schemes are used to solve the problems of low efficiency and long time consumption of polysaccharide extraction. And next, we're going to discuss about plant polysaccharides. Plant polysaccharides are a class of natural polymers composed of more than 10 monosaccharides connected by glycosidic bonds, which are widely present in natural plants, including starch, cellulose, polysaccharides, pectin, and etc. And some water-soluble plant polysaccharides with obvious resistance are called plant-active polysaccharides, which have anti-tumor, immunomodulatory, hypoglycemic, antioxidant, hepatoprotective, antiviral, intestinal regulation activities. And because of its easy accessibility, low toxicity, and biodegradability, it has become a hotspot for research on bioactive substance. And recently, a large number of new plant polysaccharides have been reported, and ginkgo biloba leaves polysaccharide is one of them. Uh, Ginkgo biloba leaves is a plant of the Ginkgo genus under the family of Ginkgoaceae, which is called a living fossil, and is an ancient tree species native to China. Uh, First, ginkgo biloba leaves are light green, fan-shaped leaves with long stalks and are used as a medical herb in China for its antitussive, blood-promoting, antidepressant, and cholesterol-lowering properties. And polysaccharides play an important role in the activity of ginkgo biloba leaves. At present, there are relatively few studies of ginkgo biloba leaves, and it indicates that ginkgo biloba leaves uh, Vegetable leaves have good antioxidant activity and immunomodulatory activity, and then therefore gingival leaves polysaccharides have a wide range of research value and space. For the activity of polysaccharides is influenced by various factors such as solubility, molecular weight, spatial structure, and etc. Some inactive or less active polysaccharides are difficult to be applied. So, chemical modification of polysaccharides provides a solution to difficulty, as it is an effective means to improve activity, which includes sulfation, salinization, phosphorylation, carboxymethylation, acetylation, and etc. Chemical modification will change the type of polysaccharide substituent, number of substituents, spatial structure, molecular weight, solubility, and etc. So as to achieve the purpose of improving the activity. And for this study, gingival leaves modified by acetylation, symbolized by AC, and carboxymethylation, symbolized by CM, and then the solubility and in vitro antioxidant activity of this modified and unmodified polysaccharides were analyzed and compared. So this provides some clues to solve the difficult problem of poor polysaccharides, activity and solubility, and also provides some reference values for the application of ginkgo biloba leaves polysaccharides. And the next, we're gonna talk about materials and methods. And for this research, the material is ginkgo biloba leaves picked from the University where the authors studied. And then ginkgo biloba leaves were washed and dried in an oven at 60 degrees Celsius and then ground into the powder for use. And for the reagents for this research are petroleum ether and butanol, chloroform, chloroacetic acid, isopropyl alcohol. alcohol, acetic anhydride, ethanol salicylic acid, hydrogen peroxide, iron 2 sulfate, thiobarbitoric acid, 3-chloroacetic acid were obtained from Chengdu Cologne Chemical at Chengdu, China. And then the other reagents, concentrated sulfuric acid, concentrated hydrochloric acid, and natrium hydroxide were obtained from Guangdong Chemical at Chengdu, China. And then soil lecithin was obtained by Marine Biotechnology at Shanghai, China. And then the last one is the PPH was obtained from around Co, Shanghai, China. And then all other relevant reagents were of analytical purity grade. And then next, we're gonna talk about ultrasound-assisted extraction. For this research, first of all, dried powder of gingibiloba leaves was added to petroleum ether with a ratio 1 and 15 gram per milliliter, and then reflux at 80 degrees Celsius for 2 hours to remove lipids and pigments. And then after reflux, CD was by filtration and dried. So 5 milligrams of the above residue was added to a certain proportion of distilled water to extract polysaccharides by ultrasound extraction under certain temperature, power, and time conditions. And then after duration was completed, the filtered collected by filtration was concentrated to 50 milliliter under reduced pressure, and then 20 milliliter of cephate reagent and butanol. Ratio of n-butanol and chloroform is 1 and 4 was added and reacted under shaking for 25 minutes to remove the protein. And then the supernatant was collected by centrifugation after the mixture was allowed to stand for 15 minutes, and the supernatant was sterilized overnight with distilled water in a 3,500 dA bag. And then finally, anhydrous ethanol was added to the dialysate to make the final concentration of ethanol reach 75%, and the solid was collected by centrifugation. And after that, the solid was washed with anhydrous ethanol, acetone, and ether in turn, and then first dried to obtain gingibiloba leaves polysaccharides. And the total sugar content was determined by phenol sulfuric acid method. And then the last one, we're going to calculate the yield of gingibiloba leaves polysaccharides with the following equation as in the screen. Yield is a weight of gingibiloba leaves divided by weight of gingibiloba leaves powder and then multiplied by 100. And then for the method, we're gonna have a single factor experiments. For this part, we're gonna have 3 factors, uh, such as ratio of liquid to materials, extraction time, and ultrasonic power. And then for this part, the resulting optimal single factor was used as a fixed condition for the next single factor experiment. So the variance of liquid to material ratio included 10 milliliter per gram, 20 and 30 milliliter. There's a various. Uh, there are 10, 20, 30, 40, and 50 milliliter per gram. But for the extraction time, included 20 minutes, 30 minutes, 40 minutes, 50 minutes, and 60 minutes. But for the ultrasonic power, included 260 watt, 252 watt, 288 watt, and then 324 watt, and then 360 watt. So for the experimental design, the liquid to material ratio, ultrasonic power, and extraction time were used as 3 factors to explore the optimal conditions for ultrasound-assisted extraction of GBLPS using RSM. Based on the result of the single factor test, 3 appropriate levels were selected for each other, and it can be seen in the table in the screen three independent variables and their levels. That one, there's three level and three independent variables, like ratio of liquid to material. There's the three levels are 15, 75, and 35. But for the ultrasonic power, uh, they are 288, 324, and last one is 360. But for extraction time, there are 40, 50, and 60 minutes. So there are some experiments with refractors and T-level were designed according to the Box-Benken central combination model using the yield GBLPS as the response value. And then in this research, we're gonna see the radiation fitting model and then represented by the following second order polynomial, and the equation is seen in the layer. E is A0, and then yeah, just like that, and then where Y is the predicted response value, and then AI, AII, and AIG are the primary term coefficients, and then quadratic terms coefficient and interaction term coefficients respectively. But for XI and XJ are independent variables. There is tasks. There's a four tests for this part, and then the first one is preparation of CM GBLPS. Carboxymethylation of GBLPS was slightly modified from the previous method. In this part, 1 gram of polysaccharides was added to 80 milliliter of natrium hydroxide with 20% and stirred for 1 hour to dissolve it fully, and then 80 milliliter of chloroacetic acid isopropanol solution with 1.2 gram per milliliter was slowly added to react at 55 degrees Celsius for 5 hours. And then after the reaction was completed, the pH value was adjusted to neutral with 2 mole per liter and then the reaction solution was sterilized with running water and distilled water sequentially for 1 day. And then ethanol was added to precipitate to obtain CmGBLPS. And then the substitution degree of CmGBLPS was determined by titration method. And for this part, 10 milligrams of CmGBLPS was added to 10 milli of natrium hydroxide solution, 0.01 mole per liter, and stirred in a water bath at 45 degrees Celsius for 30 minutes. And then the solution was titrated with 0.01 mole per liter HCl using phenolphthalein as indicator. And then we're gonna calculate the degree of substituent of CmGBLPS as symbolized with PSGM. And then the equation is 0.132 divided by 1 minus 0.058 dm is the amount of natrium hydroxide consumed per gram of sample calculated from the titration. But for the preparation of AC, GBLPS, or acetylene, is was referred to the method of C at all. And in this part, 1 gram of GBLPS was dissolved in 25 milliliter of distilled water, and its pH value was adjusted to 9 with natrium hydroxide, 10 mole per liter solution. And the next 10 milliliter of acetic anhydride was slowly added to the above solution, and the pH value adjusted with natrium hydroxide solution to keep the pH value between 9 and 10 throughout the process. And then after above operation was completed, the reaction solution was to react at room temperature for 2 hours. And then the pH value was adjusted to neutral with HCl solutions. And then finally, the above reaction solution was sterilized with running water and distilled water for 1 day in turn. And ethanol was added to it for precipitation to obtain ACGPLPS. And then the substitution degree of ACGPLPS was determined by titration method. It's the same with CMGBLPS. And then 20 milligram, 20 milligram of ACGBLPS was added to 10 milliliter of natrium hydroxide solutions, 0.0 mole per liter, and stirred in a water at 50 degrees Celsius for 2 hours. And then the Igbo solution was titrated with 0.01 mole per liter HCl using phenolphthalein as indicator. It's the same, and then the substitution of ACGBLPS was calculated. And then we're going to find the following equation as in the screen, symbolized by the SAC, 132N divided by 4,300 minus 42N, and then where N is the amount of acetyl group accumulated from the titration. And then the third one is solubility test. Determination of solubility was likely improved on the method described by Kong et al. And 40 milligram of polysaccharide sample were added to 50 milliliter containing 10 milliliter of distilled water and allowed to dissolve by magnetic stirring, 200 rotation per minute in a water bath at different temperatures. There is 5 various temperatures: 20, 40, 60, 80, and 100 degrees Celsius. And then the time consumed for complete solutions was recorded and plot linearly against temperatures. And then another 120 milligram of polysaccharide samples were taken with 10 milli of centrifuge tube, and 4 milli of distilled water was added to dissolve it by ultrasonication at room temperature for 30 minutes. And then the precipitate obtained by centrifugation of the work mixture were dried and weighed. And then the weight was recorded as gram. And then the maximum solubility was calculated in the following equation as in the screen. 120 minus x divided by 120 and then multiplied by 100. And then the last one, we're going to talk about infrared spectroscopy and nuclear magnetic resonance determination. In this part, the appropriate amounts of polysaccharide sample were grown evenly together with KBR and then pressed into a thin slice for determination by infrared spectrometer. And then a thin slice composed entirely of KBR was used as the background, and the detection wavelength was 4,000 per centimeter. And then the polysaccharide samples, 45 milligrams, were fully dissolved in 0.5 milliliter of heavy water at 99.99% in an ultrasonic water bath, transferred to a nuclear magnetic tube for NMR analysis. And then there is a determination. There's a 3 determination for this part. The first one is determination of hydroxyl radical scavenging activity. For this method was slightly modified on the previous method. So 1 milliliter iron to sulfate with 8 millimole per liter, and then 1 milliliter salicylic acid ethanol solution with 8 millimole per liter, and 1 milli hydrogen peroxide with 8 mole per liter were added sequentially to 1 milliliter polysaccharide solution with 5 variations, 0.125 milligram per liter, 0.25, 0.5, 1, and 2, and the last one is 4 milligram per liter to initiate the reactions. And then the reaction was carried out in a water bath at 77 degrees Celsius for 30 minutes. And then the absorbance of the reaction solution was measured at 510 nanometer using distilled water as a blank control and VC as a positive control. And hydroxyl radical scavenging activity was calculated according to the following equation as in the screen. SOH is 1 minus A1 minus A2, then divided A0 and multiplied by 100, where A1 is the absorbance of the sample, A2 is the background of absorbance of the sample, and A0 is the absorbance of the blank. So the second one is determination of DPPH radical scavenging ability. Mm, for this part, according to the method described by Chen et al., first of all, 4 milli of DPPH ethanol solution, 0.5 millimole per liter, and 2 milli of polysaccharide solutions with six variations, same with before, and then were mixed and reacted for 15 minutes in the dark, and then the absorbance of the above reaction solution was measured 517 nanometer using distilled water as the blank control and PC as a positive control. And then the anti-lipid peroxidation ability was calculated according to this equation, like in the screen, as the PPH 1 minus B1 minus B2 slash B0 multiplied by 100, where B1 is the absorbance of the sample, B2 is the background absorbance of the sample, and B0 is the absorbance of the blank. So for the last one is antilipid determination of antilipid peroxidation ability. The antilipid peroxidation ability was determined by referring to the method of Chen et al. And then this one is 2 milli of soy lecithin solution configured from PBS with pH 7 and 0.4 milliliter of iron to sulfate solution with 10 millimole per liter, were added sequentially to 2 milli of polysaccharide solution. And then this reaction was carried out in 37 degrees Celsius water bath for 50 minutes. And then after the reaction was complete, the reaction liquid was cooled at room temperature, and then 1 milliliter TCA, 20%, and 1 milliliter baric acid, were added and transferred to a boiling water bath for reaction for 20 minutes. And then the reaction solution was allowed to cool to room temperature, and the superintendent was obtained by centrifugation. And then the absorbance of the above supernatant was obtained by centrifugation. It was measured 535 nanometer using VC as a positive control, and then PBS solution as a blank control. And then the antilipid peroxidation ability was calculated according to the following equation. SLP is 1 minus C1 minus C2 divided by CO, and then multiplied by 100. So C1 is the absorbance of the sample, C2 is the background absorbance of the sample, and C0 is the absorbance of the blank. So overall, the equation is the same, just the symbol is different. The next topic is result and discussion. The first one, we're gonna discuss about the effect different factors on ultrasound-assisted extraction efficiency. So in this part, there are three different factors, such as ratio of liquid to material, ultrasonic power, and extraction time. And the graphic of each factor is three different. So, we're gonna discuss the first one for the ratio of liquid to material. The yield of GBLPS increase faster with the increase of the liquid to material ratio at lower liquid to material ratios. So, this may be explained by the increase in sulfur ratio result in higher osmotic pressure of the cells, and thus accelerating the efflux of intracellular material. And on the other hand, the increase of sulfan volume led to a larger area of ultrasonic actions, which result in greater ultrasonic efficiency. And for this trend, uh, the liquid materials, the ratio of liquid to material reached 25 gram milliliter per gram, and then at that point, uh, the yield of GBLPS reached the maximum value or the extreme value, and after that, the yield of GBLPS gradually decreased. The liquid to material ratio continued to increase, which may be due to the excessive liquid to material ratio reduce the intermolecular interactions, resulting in a significant reduction of ultrasonic penetration. And then the picture is in the left side. But for the second factors is ultrasonic power. The yield of GBLPS increased sharply when the ultrasonic power increased from 200 to 300 watt. And then the increase of yield of GBLPS leveled off. And with the increase of ultrasonic power, the computational effect, thermal effect, and mechanical effect were enhanced, which led to the increase of LGBLPS. However, when the ultrasonic power was too high, the polysaccharides in the solvent were subject to ultrasound, leading to the degradation of polysaccharides. And these two mechanisms may be responsible for the trend of GBLPS yield. And the picture is uh, and the screen at the center. And then for the third one, is extraction time. The yield of GBLPS increased rapidly with the increase of extraction time. And reached the extreme value at 50 minutes. Subsequently, the yield of GBLPS to decrease with the increase of extraction time. This trend may be the result of a combination of two factors. On the one hand, with the increase of time, the accumulation of thermal effect accelerated of the outflow of polysaccharide from raw materials, so the yield of GBLPS increased. On the other hand, the increase of extraction time caused the solution concentration to become larger, resulting in a smaller cellular osmotic pressure. So at the same time, the polysaccharide in a solution were degraded due to the time accumulation effect, so the yield of polysaccharide decreased. And then the second one, we're gonna discuss about optimization of ultrasonic extraction condition. In this part, uh, we're gonna find the model fitting and statistical analysis. The matrix of RSM was designed by design expert 12 software. The experiment was randomly divided into 17 groups. And this part is below at the screen in the right. And then the experiment of its 12 groups were interactive experiments, and the other 5 groups were central repeat experiments for error analysis. And then through multiple regression analysis, the relationship between the response value and the factor was obtained as follow. And then for the result of statistical analysis of the model are shown in the table in the left side. R value is used to detect the overall significance of this model. And in this model, the R value was 260.84, which indicated that the model is significant. But for p-value is used to detect the significance of items, and items are considered significant when p-value is under 0.05. Under this condition, the p-value of the model terms was less than 0.0001, indicating that the item is highly significant. Meanwhile, all primary terms were significant, while only AC was significant in the interaction time. The lack of fit F value of 1.75 mean that it is not significant relative to the pure error. The value of coefficient of variation or CV was only 0.6239%, which indicated that the experiment is well reproducible, and the model is reliable. In addition, the coefficient of determination R square is used to evaluate the quality of the model. So when the value of R square is closer to 1, it indicates that the regression equation fits the observation better. Their square values and adjusted R square values in this model were 0.997 and 0.9932 respectively, which indicated that only 0.68% of the total variance cannot be explained by this model. So the model has a goodness of it. And in summary, the model was established successfully and was statistically significant. And we're gonna discuss about confirmation of optimal condition. In this part, the response surface of three dimension or 3D can be used to evaluate interaction between the two vectors, and as shown in the picture at the screen. Uh, and then part which indicate that interaction between liquid to material ratio, and then the first one in the left side for picture in interaction between ultrasonic power with ratio of liquid to material, and centered attraction time with a ratio of liquid to material, and then the right side attraction time with ultrasonic power. So in addition, the color change rate of the counter line can reflect the significance of each factor on the response value. It is obvious that the liquid to material ratio had the greatest influence on the yield of UBLPS among the three factors. However, this is influenced by the selection of factor levels. In this model, factor A was selected through levels with a wide range. However, both factor B and factor C were selected at a narrower range for reasons such as equipment and efficiency. So this result in a large difference in the significance of the response values for the different factors. And based on the response surface analysis, liquid to material ratio of um, the optimal assessment condition were obtained as follows: liquid to material ratio of 28.449 milliliter per gram, and ultrasonic power of 339 and 0.85 watt, and extraction time of 51.51 minutes, and the predicted value of yield of 5.4% under this condition. For the verifications of optimal condition, uh, the optimal condition predicted by the model would be selected for the experiments. So the experimental condition will be slightly modified for the convenience of the experiments. Liquid to material ratio of 30 milliliter per gram, listening power of 340 watt, and extraction time of 50 minutes. And then the experiments were carried out 3 times, and the first yield of UBLPS was 5.37% under this condition, which was in good agreement with the predicted value. So the model is adequate and accurate. And then next, we're gonna discuss about analysis of chemical modification. In this part, CM, GBLPS, or carboxymethylation Ginkgo biloba leaves Ginkgo biloba leaves polysaccharides was obtained by a reaction using chloroacetic acid as the carboxymethylation reagent. And then the yield, this is based on principle of using alkali to alkalize the polysaccharide, and then using the electrophilic nature of electroacetic acid for the esterification reactions. And the yield of CMGBLPS was 89.5%. But for the sugar content measured by phenol sulfuric acid method was 49.6%, less than 72.5% of GBLPS. and then which is similar to the conclusion of research uh, of Wang et al. The reaction in acidic and medium temperature condition caused the hydrolysis of some polysaccharides, so the sugar content decreased. But for the degree of substitution of CMG-BLPS calculated by the formula was 0.72, which is high degrees of substitution, and it is related to the amount of carboxy methylation reaction temperature, reaction time, and other factors. But for the yield of AC, GBLPS or acetylation uh, have 58.8%, which is lower than the result of research C at all. And for the sugar content of ACGBLPS was 55.2%, which is slightly lower than of GBLPS but higher than CMGBLPS. So the acetylation reaction is a nucleophilic substitution reactions, and the reaction process is more sensitive to the pH value, needs to be controlled between 9 to 10 to maintain an alkaline environment. The stability of the pH value has a large effect on the yield and polysaccharide content. So the acetylation degree of substitution calculated by the formula degree was 0.35, which is in a more reasonable range. And then next, we're gonna discuss about analysis of solubility. It is part macromolecular polysaccharides are almost insoluble in organic solutions, and some polysaccharides have a certain solubility in water. Solubility is an important index to evaluate the application value of polysaccharides. So the solubility of three polysaccharides was evaluated by dissolution rate and maximum dissolution amount. Uh, the dissolution rate of the three polysaccharides was gradually accelerated with the increase of temperature, and the fastest growth rate was found in the range from room temperature to 40 degrees Celsius, and it shown in figure at screen. And then the dissolution rate of CMGBLPS was not much different from that of GBLPS at lower temperatures, but it was faster than GBLPS at higher temperatures, while SGBLPS dissolved faster at all temperature compared of GBLPS. And then the maximum solubilities of GBLPS, ACGBLPS, and CMGBLPS calculated according to the method of 2.8 were 39.87%, 60.13%, and 44.22% respectively. So, the mechanism by which chemical modification enhanced the solubility of polysaccharides is thought to be that the modification group changed the spatial structure of the polysaccharides, causing the aggregated polysaccharide molecules to strengthen more, which results in the exposure of more hydrophilic hydroxyl groups. It is obvious that ACGBLPS and CMGBLPS show not only improvement in the dissolution rate but also a substantial increase in the maximum solubility, and this is also consistent with what has been reported. And in addition, different degrees of substitution can have different effects on polysaccharide solubility. So, Kurita et al. Concluded that an acetylation degree of substitution between 0.4 and 0.6 is most favorable for increasing solubility, and the solubility of ACGBLPS was greater than of CMGBLPS, which may be due to the difference in substitutions. And then next, for analysis of infrared spectroscopy. In this part, we used to identify the functional groups and specific structures present in the polysaccharides. And the result of the infrared spectroscopic identification of the three polysaccharides are shown in picture at the screen. The first one is the broad peak at the first one is the line indicated by black color. The broad peak at 3,270 and 97 was attributed to the OH bone, stretching fibration of the hydroxyl group on the sugar ring of GBLPS. And the smaller peak near at 2,923 per centimeter was attributed to the CH bone stretching, vibration, and of the methyl and methylene groups of GBLPS. So the peak is at 1,603 per centimeter and 1,411 per centimeter were attributed to the stretching vibration of the carboxyl group, which indicated the possible presence of uronic acid in GBLPS. So the peak present at 1,070 and 25 per centimeter in the fingerprint region was attributed to the asymmetric stretching vibration of the COC bond, which is the characteristic peak of Pyranose ring. And then compared with GBLPS, the ACGBLPS indicated by blue color showed a new peak at 1,150 per centimeter, which is the characteristic peak of the ester group. And it was caused by the stretching vibration of CO bone of the acetyl group. And in addition, the peak intensity of the peak at 1,626 per centimeter became stronger, which was caused by the stretching vibration of CO in the acetyl group. This change proved that the acetylations of the polysaccharides was successful. And then for lithium CBLPS, indicated by orange color, the peaks at 1,588 per centimeter, 1,415 and 1,325 per centimeter were attributed to the stretching vibration of the CO bone, the symmetric stretching vibration of the COO bone, and the variable angle vibration of the CH bone, respectively. And they are characteristic absorption peaks of carboxymethyl. This characteristic indicate that the carboxymethylation of polysaccharide was successful. So it is noteworthy that the chemically modified polysaccharides showed a change in shape and chemical shape in the characteristic absorption peak region of the hydroxyl group around 3,300 per centimeter, indicating that the chemical modification had changed the number and association degree of the hydroxyl group. Besides, in most other regions, the three polysaccharides had similar peak patterns, which proved that the chemical modification didn't change the main structure of the polysaccharides. And next, analysis of NMR. The three polysaccharides were evaluated by NMR analysis. The anomeric carbon signals of GBLPS were concentrated in the region from 95 to 110 ppm. And then there were five more obvious signals in these regions, which reflected that GBLPS has complex glycosidic bond linkage. The region between 50 and 90 is the distribution region of the C2 to C6 signals of monosaccharide residues. The signal at around 60 were attributed to the C6 signals of the hexose. The strong peak at 16.78 in the high field region was attributed to the signal of the primary carbon, which indicate the presence of deoxygenated sugar residues in the structure of GBLPS. Based on previous studies, the signal was inferred to be the C6 signal of rhamnose in the low field regions. The presence of 175.19 indicate the presence of acidic groups in the structure of GBLPS, which is consistent which the result of infrared spectroscopy. And then compared with the 13C NMR of GBLPS, ACGBLPS increased the signals at 173 and 170.27 in the low field regions. It indicates that the picture in the left uh, at the top, and which were attributed to the acyl carbon of the acetyl group. And at the same time, the signal of 21.06 was increased in the high field region, which comes from the primary carbon and was attributed to the signal of the methyl carbon atom on the acetyl group. Uh, the shielding effect of the carbonyl group makes it shift to lower fields compared to the normal methyl carbon signal. And then, in addition to this change, most of the signal in the region from 55 and 110 ppm were chemically shifted due to the introduction of acetyl groups. Looking at the signals in this region as a whole, it was clear that the signal of ACGBLPS overlapped more severely compared to that of GBLPS. This is caused by two reasons. On the one hand, the introduction of the acetyl groups as an electron withdrawing group weaken the electron withdrawing effect of the hydroxyl group, so which indirectly led to the narrowing of the chemical shift gap between carbon atoms. On the other hand, as discussed, the stretching of polysaccharides by acetylation weaken the effect of special effects on chemical shift. Similarly, these changes were also reflected in the 13C NMR of CMGBLPS, which have a much stronger signal overlap in this region than the acetylated polysaccharide. And at the same time, two new characteristic group at 177.32 and 178.69 appeared in the 13C NMR of CMGBLPS due to the introduction of the carboxymethyl group. And this result was similar to that obtained by research of Yang et al. In addition, chemical shifts are used to determine the derivatization state, but this only applies to structurally simple polysaccharides. Even so, it is still possible to get some useful information from it. The signal of the chemically modified polysaccharides around 60 were significantly displaced. As inferred above, this region was mainly attributed to the C6 signals of monosaccharide residues, which implied that C6 is an important chemical modification site. This is reasonable in terms of chemical structure because C6 carbon has a smaller rigidity and larger uh, spatial extent than carbon at other positions. And of course, the chemical shift of the signal in the range of 65 to 90 ppm also suggested that the chemical modification occurred at other sites at the same time. In conclusion, the NMR analysis once again demonstrated that two chemical modifications were successful. The next one, we're gonna talk about in vitro antioxidant activity analysis. And this part, there is three segment. The first one, hydroxyl radical scavenging rate. Uh, in this part, uh, was tested by Fenton reaction system. Hydroxyl radical is a kind of highly oxidizing reaction oxygen species, which has attracted wide attention because of its correlation with aging and the pathology of certain diseases in a human body. So, hydroxyl radical scavenging activity is one of the most commonly used index to evaluate antioxidant activity in vitro, as shown in figure at the screen in the left side. So there was a significant positive correlation between the polysaccharide concentration and the scavenging rate. So when the concentration of UBLPS reached 2 milligram per milliliter, the scavenging rate basically reached its maximum value, which was not very satisfactory. Hydroxyl radical scavenging ability is related to the properties of the material itself, which is influenced by various factors such as solubility, molecular weight, and spatial structure of the material. Similar hydroxyl radical scavenging activity had also been found in previous literature for polysaccharides from ginkgo biloba leaves. And the hydroxyl uh, radical scavenging activities of the chemically modified polysaccharides were significantly improved at most concentration, and the effect of carboxymethylation modification was more significant. CMGBLPS reached half the scavenging rate of positive control at a concentration at 4 milligram per milliliter. At the same time, it should be noted that the scavenging rate of ACGBLPS and CMGBLPS still tended to increase when they reach their maximum concentration. Which is different from GBLPS. Possible reason for the ability of chemical modification to enhance hydroxyl radical scavenging were considered to be 2 points. One is that the introduction of the modification group enhanced the hydrogen donating capacity of the polysaccharides, leading to the enhancement of the activity. Although this point had been demonstrated in most studies, the different derivations showed large difference. In this respect, possible relation modification tended to be more prominent. Second, the introduction of the modification group changed the spatial structure of polysaccharides, result in more reaction sites exposed. And this mentioned before investigation of solubility. Based on this, some seemingly complex conclusions are well explained. For example, different chemical modification sites have different effects on an antioxidant activity, which may be caused by the different benefits of different chemical modification sites on enhancing a hydrogen supply capacity. The effect of different degrees of substitution on antioxidant activity may be attributed to the second reason mentioned above. In this experiment, CMGBLPS exhibit superior hydroxyl radical scavenging ability to ACGBLPS. However, in the solubility experiment, ACGBLPS showed better solubility than CMGBLPS, and indicating that the acetylation modified polysaccharide had more hydrophilic hydroxyl groups exposed. The first mechanism played a decisive role in these experiments. Overall, both carboxymethylation modification and acetylation modification were effective in enhancing the hydroxyl radical scavenging activity of GBLPS. And then the second one, we're gonna talk about DPPH radical scavenging rate. This part is shown in figure at the screen in the center side. On the whole, the scavenging activity of these polysaccharides for the DPPH radical was extremely low compared to positive control. Locally, acetylation showed a greater enhancement of the DPPH radical scavenging ability of GBLPS. This boost still tends to increase at the maximum concentration. This implied that greater DPPH radical scavenging activity can be obtained by increasing the concentration of ACGBLPS. And in contrast, the enhancement of DPPH radical scavenging ability by carboxymethylation was very limited, and its scavenging activity basically reached the maximum at a concentration of 2 milligram per liter. The BPS radical is a relatively stable free radical, and it is generally believed that polysaccharides achieve its scavenging in a form of single electron transfer. And under this mechanism, polysaccharides are required to have strong electron donating ability. So GBLPS is not a good electron donor, but acetylene modification can effectively improve the electron donating ability of polysaccharides. In conclusion, acetylation has the ability to enhance the PPH scavenging activity of polysaccharides to a certain extent, but it is limited by the poor DPPH radical scavenging ability of GBLPS itself and doesn't have a promising application in this regard. So the last one is lipid peroxidation scavenging rate. The anti-lipid peroxidation ability of the three polysaccharide was tested using lipid peroxidation induced by soy lecithin. Lipid peroxidation refers to the oxidative degradation of polyunsaturated fatty acid and lipids, which is an oxidation that is harmful to the human body. During this process, a large number of different free radicals are generated, and polysaccharides indirectly acts against lipid peroxidation by inhibiting these free radicals. Uh, in a system, the activity of the polysaccharide modified by acetylation and carboxymethylation was improved to a certain extent at all concentrations, and the activity grew faster at with increasing concentration before the concentration of 2 milligram per liter and the activity growth level of after 2 milligram per liter. However, there was still a gap compared to the positive control. Notably, the enhancement of antioxidant activity of GBLPS by acetylation modification and carboxymethylation modification didn't remain constant in the three in vitro antioxidant experiments. And this may be due to the fact that different in vitro antioxidant experiments have different reaction mechanism, while different mechanical modification have different effects on the properties of the same polysaccharides. In addition, from the above discussions, it can be seen that the factors affecting the antioxidant activity of chemically modified polysaccharides are various, and the previous studies also shown uneven levels. And therefore, we conclude that chemical modification has some ability to enhance the antioxidant activity of polysaccharides, but for the extent of enhancement is not controllable. It is related to various factors such as degree of substitution of chemical modification, substitution sites, and substitution group, and the reaction mechanism of the antioxidant experiment itself. And this needs to be supported by more accurate and complete data. So for the last, for the conclusion, there are several parts. And in summary, the condition of ultrasound-assisted extraction of GBLPS were optimized by RSM. And the optimal yield of GBLPS was 5.37% at a liquid to material ratio of 30 um, milliliter per gram and ultrasonic power of 340 watt and an extraction time of 50 minutes. And CMGBLPS with a substituent degree of 0.72 and ACGBLPS with a substituent degree of 0.5. And then uh, the solubility analysis show that the chemical modification could effectively improve the solubility of polysaccharide with a better effect of acetylations. Uh, and of course, infrared spectroscopy and NMR analysis proved that the chemical modification could was successful and revealed some structural features of acetylation and carboxymethylations. In vitro antioxidant experiments showed that acetylation modification could effectively improve the hydroxyl radical, the PPH radical, and lipid peroxidation scavenging ability of polysaccharides, which uh, while carboxymethylation modification could only effectively improve the hydroxyl radical and lipid peroxidation scavenging ability. To close this presentation, I'd like to thank you for watching and listening to this presentation, and hopefully this presentation can be more useful uh, to anyone who hear it. Thank you.